In this video, we're going to cover section 8.4, oxymercration, demercration. As we saw in 8.3, acid-catalyzed hydration can be used to achieve a Markovnikov addition of water across an alkene. But if carbocation rearrangements are possible, this will produce a mixture of products. So as a result, this is an inefficient method for adding water to an alkene. An alternative method for achieving Markovnikov addition of water across an alkene without carbocation rearrangements is referred to as oxymercration demercration. So as you can see in this example, starting from an unsymmetrical alkene, we're going to end up with Markovnikov addition of water. That is, the hydroxyl group will be located and form a covalent bond with the carbon that was more highly substituted in the original alkene. Now notice how this reaction is carried out in two steps. The first step we refer to as oxymercration, and then a second step, separate from the first, is what we refer to as demercration. And so using these numerical bullets, we're able to separate these two reactions, but we show them on a single reaction arrow. So when you see reaction arrows drawn in this way, where you have numerical bullets above and below, they represent individual reactions, specific reactions. So let's look at more details for this reaction so we can understand A, why we have Markovnikov addition, and B, why we avoid rearrangements. So the process begins with a specific reagent known as mercuric acetate, and it's given by this formula, Hg bracket OAC, representing this acetate group, and we have two of those groups attached to the mercury centers. You can see here mercuric acetate, and what will happen to this reagent is that it will dissociate to give you the mercuric cation, and this is the reactive species that will interact with our alkene in the formation of our new alcohol. So the mercuric cation, as shown, this is a very strong electrophile, and so it will be open to nucleophilic attack by even weak nucleophiles such as alkenes. So the pi bond of an alkene or an alkyne will undergo nucleophilic attack onto this strong electrophile. So when the pi bond attacks the mercuric cation, we refer to this intermediate as not a carbocation. And that's because this mercury atom here is really interacting with both of those carbon centers. In a sense, you can draw a resonance structure that shows this mercury atom bridging those two carbons. So here's the mechanistic step for that oxymercration. We see that we're starting from the pi bond, drawing our curved arrow directly to the mercury center. This is the resulting structure. So we form a new bond to mercury. The carbocation, which doesn't really form, this is, again, this is a resonance hybrid, and there's two structures representing this hybrid. So we never really have a true carbocation for the mercurinium ion, as it's referred to. So we see we have a partial positive charge associated with this carbon, and this is where the eventual OH group will end up. So this fairly exotic species is known as the mercurinium ion, and it has two resonance structures which represent the resonance hybrid for it. So let's look at what happens next once we form the mercurinium ion. How do we get to this addition of water? So it's at this point that we've generated this mercurinium ion. It is now open to nucleophilic attack by other species. So we're talking about hydration, so we're going to use water as our nucleophile, but you could also use alcohols like methanol and ethanol if you wanted to produce ethers. So what will happen in either case is that you'll have nucleophilic attack onto that more highly substituted carbon, because that's where that partial positive charge is generated due to, when we looked at the resonance hybrid, we have that partial positive charge associated with that carbon center, unlike the other neighboring carbon center. So what we observe is that the more substituted carbon, which bears that partial positive charge, it will undergo nucleophilic attack, or it will be attacked by an incoming nucleophile. Because that mercurinium ion is really a resonance hybrid of two structures, we never fully form a carbocation, and therefore we can't undergo any carbocation rearrangements. You can't have a rearrangement if you don't form a carbocation. So that's why we see this very strict regiochemistry for the oxymercation reaction. So nucleophilic attack will take place at the more highly substituted position due to that partial positive charge, and it is that first nucleophilic attack of water or an alcohol that is leading to the Markovnikov addition that we'll observe in our final product. Now, the second step in this reaction, the demercuration step, which involves a strong hydride delivering reagent known as sodium borohydrate, this sodium borohydride is used to basically remove that acetyloxymercury group. So this group here, we want to remove this and we're going to replace it with a hydrogen. And the source of the hydrogen is really a hydride from sodium borohydride. And it's believed to undergo this reaction via a radical process. Now, at this point, I hope you're not getting too concerned about the mechanistic details of this. I would never ask you for the specifics of this particular reaction, but we're going through some of the details of the mechanism so that you can understand why we observe Markovnikov addition for the addition of water or alcohols to an alkene, and why it is we don't see carbocation rearrangements. So it's not a testable reaction in terms of the mechanistic details, but the outcomes, the major products that you obtain from this reaction, that is something that I would like you to know. So now, at this point, again, we have the nucleophile has attacked the mercurinium ion, and the demercuration step is going to result in the final formation of the alcohol. We don't observe any rearrangement as a result of this mercurinium formation, and we don't observe any real stereochemical control in this reaction either. And that's because with the oxymercation step and demercuration step, there's somewhat of a scrambling of any stereochemistry that may have been present in that first step. So although that nucleophilic attack, if that's a chiral center, may lead to some stereochemical product, meaning we could have a configuration assigned to that particular oxymercation step product. When we go through the demercuration step, we really have no control over how that occurs. And so that's what we're referring to as scrambling. We don't have any specific control over that reduction step. So as a result, that hydrogen or hydroxyl group, they may be on the same side as one another. They may be cis or trans. We really don't know. If a new chirality center is formed, as shown in this particular example, where we do have a chiral center right here, we would expect a racemic mixture, meaning we're going to get a mixture of RNS and enantiomers from this reaction. So we don't have the same stereospecificity or stereoselectivity that we've observed previously. So this is the second of 3 hydration of alkene reactions that we will look at. Why this one is important primarily is due to the fact that A, you end up with Markovnikov addition, as we saw with acid catalyzed hydration, but the benefit of oxymercation demercuration is that we do not observe carbocation rearrangements because we don't form a carbocation. We form the mercurinium ion, and it is not open to rearrangement as we saw with other carbocation species with the acid catalyzed hydration reaction. So those are the two reasons why this reaction is synthetically useful. So if you have any questions about oxymercration, demercration, by all means, send me an email. Thank you.